very good morning. I welcome you all to the NPTEL course on Electrical Distribution System Analysis. And today we are going to talk about distributed generation integration issues in distribution systems. Now, when you talk about distributed generation, that means DGs, refer to electricity generation within or close to the point of use as opposed to centralized generation at large plants. The main focus here, generators, those are not necessarily of the rating megawatt scale, but even for kilowatts and hundreds of kilowatts and even thousands of kilowatts can be connected a different distribution system to cater the local load. This concept is key in modern power systems where there is a shift towards using smaller and more localized energy sources. For an example, if you like to have rooftop solar or maybe a small wind farm, then probably this can be accommodated at your load terminal immediately itself. Now, distributed generation is becoming increasingly significant for several reasons, and that could be the first one, reduced transmission losses. So, it is expected when the energy is not flowing a long distance and you could able to generate at local point, then certainly the transmission losses are expected to be less. It is also being told that distributed generations increase reliability. DG can improve the reliability of power supply, especially in remote or isolated areas. There are a bit of environmental benefits. Many DG systems use renewable sources, thus reducing greenhouse gas emissions and dependency on fossil fuels majorly. Support for grid during peak load is an important issue. That means DG can provide additional power during peak demand as well as reducing the stress on the main grid. Now, empowering the consumers, DG enables consumers to produce their own energy, potentially turning them into net energy producers. Now, if you look into this diagram, the distributed generations, they are majorly categorized into different vectors, and one of them probably can be classified into DG connection point, where depending upon the transmission network as well as distribution network, they are being categorized. At the point at which they are being connected, that could be of low voltage or medium voltage or high voltage, and based on the connection point, we can say DG connected to transmission network, DG connected to distribution network, and then the second one is based on capacity. Now, many times we are a bit confused that which is a small DG and which is a large DG. Now, there are many terminologies are being used during technical discussions. One category is known as micro DG, small DG, medium DG, and large DG. Now, micro DGs are those distributed generations having a rating or a capacity varying from 1 watt to 5 kilowatt. This is known as your micro DGs. Small DGs which vary from 5 kilowatt to 5 megawatts, and medium DGs which are 5 megawatt to 50 megawatts. So probably they are a bit large in size, and finally the large DG as close as thermal power plants, which is 50 megawatt to 500 megawatts. Now, based on technology, the distributed generations are also classified into renewable, non-renewable, and storage. Now, if you look into the interconnection issues, then there are two major categories. One is supply of active power, and the second one is ancillary services. Ancillary services further are of different categories: frequency regulation, reverse requirements, reactive power requirements, system security, power quality, and voltage regulation. And finally, we can say it is a customer owned distributed generation, independent power producer, that is IPP based DG, and finally utility own. So this is what the whole history of classification of distributed generations. Now, if you look into the distributed generation technology in specific, the moment you talk about DG connection points, there are reciprocating engines. They're either diesel type or gas type. Then we have gas turbine type, combustion turbine type, and micro turbine types. Now, in case of renewables, we have hydro, either it could be small or micro. Then we have wind. Then we have actually solar. Solar could be solar PV or solar thermal. Then we have geothermal, biomass, and tidal. Now, the last category, which is ESS, electrical energy storage technology. So we have one category which is stationary ESS, and the other one is movable ESS. Now, in case of stationary, we have mechanical type, which is pumped hydro and CAS flywheels, electrical type, which is double layer capacitor or SMES, chemical, which is hydrogen electrolyzer, fuel cell, SNG, thermal, sensible heat source, molten salt, electrochemical, which is lead acid, lithium ion, NAS, NIMH, NICD, flow batteries, etc. Now, in case of movable electric, we can think of your electric vehicle battery, hybrid electric vehicle applications, as well as plug-in EV devices. Now, if you focus on the installed capacity and generation in India, specific to the year 2023, which is recent past, as you could see from the diagram, the installed capacity, which is close to 415 gigawatt, and you can easily observe approximately 16% installed capacity are from solar energy. And the wind is close to 10%. And similarly, the gross generations, which are close to 1624 BU, British units, and the PV generation, which is contributing approximately 6.24% of its total gross generation, and wind, which is contributing close to 4.4%. So, as a whole, if you compare, the installation capacity is close to 25 to 30% of the total installed capacity in India, and approximately 10 to 12% gross generation available to us from wind and solar energy. So, these are the two distributed generation systems playing a critical role in Indian power systems. If you see the way the solar and wind installation happening in the financial year 2023, as you could see, the contribution from solar is extremely high, and the wind is also equally giving competition to its contribution in DG segment. But one thing is very clear: installation of renewable energy in specific to solar and wind are significantly important, and they are contributing to the Indian power system significantly. Now, let us focus on the specific type of distributed generation, that is wind power generation. Now, wind power generation, there are of two types. One is horizontal axis wind turbine, the other one is vertical axis wind turbine. Now, a wind energy conversion system, is popularly known as WCS, converts wind energy to mechanical energy, which is then used to generate electricity via an electrical generator. Now, there is a standard equation that reflects the magnitude of power which is available to me. That means the power equation of the wind turbine is given by the equation P, which is equal to half of rho A VQ Cp, where P is the power generated, rho is the air density, capital A is the area swept by the turbine, V is the wind velocity, Cp is the power coefficient that represents the turbine's efficiency in converting the kinetic energy of the wind into mechanical energy. So, if you know all the variables, probably you can approximately calculate the amount of P that may be available to you out of a wind generation. Now, these are different arrangements. So, wind power generations are of different technological arrangements you can foresee. The first one is so called squirrel cage induction generator, where you have the turbines followed by a gearbox, followed by a generator, SGIG, and then transformer, then connected to the main grid. And this is a fixed speed machine. We have one more category known as variable resistance bound rotor induction generator. The mechanism is almost similar. However, we can see a doubler IG which contributes to variable resistor, and finally through a transformer the energy has been fed to the main grid. One of the most popularly deployed wind turbine today is known as doubly fed induction generator, so called DFIG. We have the turbines followed by a gearbox and then your generator and then finally transformer to the main grid. One more category, which is synchronous generator with full power converter. Unfortunately, this has not seen its kind of footprint across wind power generators, but it is upcoming, and this is an equally important wind generation architecture where you have the turbine and then generator, then converter, and then transformer to the main grid. Now, there are few important arrangements, that is gearbox equipped wind turbine with a full power converter and medium high speed synchronous generator. And the other one is gearbox equipped wind turbine with a full power converter and high speed asynchronous generator. Now, when you talk about a drivetrain arrangement in wind turbine, can vary typically encompassing three main types, that is direct drive, geared, and hybrid system. Now, when you talk about direct drive, means your turbine axis which has been directly connected to your generator. So, direct drive system eliminates the need for a gearbox, connecting the rotor directly to the generator. Now, geared system use a gearbox that can help you to increase the rotational speed from the rotor to the generator, allowing for a smaller and lighter generator. Hybrid system combines elements of both balancing efficiency and complexity. Now we can move to the next variety or the type of renewable source based DG technologies, that is solar photovoltaic PV. Now, similar to wind turbine, in case of solar PV, the power equation which has been given by P, which is nothing but A G eta 1 minus beta times T minus T reference, where P is the electrical power output of a PV panel, A is the area of the solar panel, G is the solar irradiance, sigma is the efficiency of the solar cells, beta is the temperature coefficient of the panel, and T is the operating temperature of the panel, and T reference is the reference temperature, which is usually considered to be 25 degree Celsius. Now, solar photovoltaic PV is an advanced technology for converting solar energy into electrical energy, and it is really too competitive today considering its efficiency. Now, it involves the use of photovoltaic cells typically made from semiconductor materials like silicon that generate electricity when exposed to sunlight. Now, the solar photovoltaic PV system, as you could see, I think these are the panels which are exposed to your sunlight with a specific inclination, and then this DC power which has been produced from those panels being converted into AC, all right, and then that has been fed to residential loads. But if it is quite enough not to consume locally, then probably this can be fed back to the distribution grids. Depending upon the size of the solar photovoltaic or the magnitude of energy that is available to me at different voltage level, this solar photovoltaic energy can be penetrated into different voltage level of the distribution systems. Grid connected PV systems are always linked to the public electricity grid through an inverter, as photovoltaic panel only generate DC. The inverter's role in this system is crucial because it maximizes the DC electricity extraction from the panel and convert it into alternating current. This system typically feature a kilowatt hour meter, that is kWh meters, to record the flow of electricity between the system and the grid. And they might utilize net metering, allowing surplus electricity to be fed back to the grid. So when you talk about anything which is having net metering system, so that means the PV energy which is slightly more than the minimum energy requirement of that system. So in that case, those excess energy can be given back to the grid. We can also store those energy through a battery system, but considering it is too expensive, probably the net metering system seems to be a practical option for any small system to get connected with the main grid. Now, distributed generation integration issues in distribution system, there are many obligations. One important factor is financial cost. Means when you go for your own system or integrating with renewable energy systems, we need to see that whether this is financially viable or not. Most of the cases, anything which is available to you through a main grid, which is either coming from nuclear power plant or hydro or solar from a main system, they're reasonably economic. However, the solar PV system is very expensive, but over a period of time, the cost has been reduced drastically. So now it is quite encouraging for all of us to get into solar PV system with turbines and probably for some extent batteries in next 5 to 10 years time. Distributed generation system, especially those harnessing renewable energy sources like solar PV and wind turbines, face challenges due to higher initial cost compared to the large centralized power plant energy cost. Now, tentatively, the solar PV system, if you analyze the cost of solar PV system in India typically ranges from 40,000 rupees to 50,000 per kilowatt, which is quite high. This cost includes the solar panels, inverters, batteries, and as well as off-grid or hybrid mode arrangements, mounting structures, and other balance of system components. In contrast, the cost of large-scale solar farms is generally lower, which is around 35,000 to 45,000 rupees due to economics of the scale. So if you increase the size, then probably the cost may reduce by 10 to 20%. Now, similarly, case of the wind turbine, the small scale wind turbines for DG application cost around 50,000 to 80,000 per kilowatt in India. This cost include the turbine, tower, installations, everything. However, if you go for a large wind farm, then the cost may reduce to 60 to 70,000 rupees due to bulk purchases and more efficient logistics and installation processes. Now, in case of battery energy storage system, that is BSS often paired with solar PV in DG systems, because for solar PV, which is quite unrealistic of its production, so we need to store at least 4 to 5 hours a day through your battery mechanism, and which is a high initial cost. So if you combine battery and PV, then that is going to be very, very high in cost. A typical small scale lithium ion battery system might cost around 7,000 to 10,000 rupees per kilowatt hour. In contrast, large scale energy storage projects can achieve lower cost due to its volume. Once again, the life of the battery, which may vary from actually 10 to 30 years, so depending upon the life, the cost also may play a crucial role. Now, when you compare with a large central power plant, especially superthermal power plants or supernuclear or probably a large hydropower plants, traditional large scale power plants like coal fired or natural gas plants have lower per kilowatt installation cost in India. For an example, a coal power plant might have a cost of around 60 lakhs to 80 lakhs per megawatt. That is 6,000 to 8,000 rupees per kilowatt, which is significantly lower than the per kilowatt cost of small scale renewable DG. Now, the high capital cost of DG system in India can be attributed to several factors. High equipment cost due to import dependency, especially for high quality solar panels and wind turbines. Smaller scale projects leading to higher per unit cost due to lack of economics of scale. Challenges in financing for small scale projects, which often face higher interest rate, that may also lead to the increase in cost. So to address these challenges, probably the government of India is promoting different schemes, a bit of waiver in interest rates, subsidies are being encouraged. But still, I think we need to promote this technology considering the cost viability of these projects. Now, when you talk about predictability of power output, now the overview of market dynamics, which is slightly different. In electricity market, entities accessing the transmission grid, termed as access responsible parties or program responsible parties, must sign contracts with the system operator. Now, there is one issue, like probably if you go for a large solar or a wind park and you produce huge amount of energy, but you must have a buyer, okay? And also you may experience bit of uncertainty in your generation. So you cannot participate in a open competition or a bidding process when your own generation is not certain. So I think probably that need to be seen as a larger perspective, how to encourage or accommodate renewable energy owner into market. These parties are responsible for maintaining a balance between their power injection into the grid and their withdrawals under the stipulation of the grid code. Now, the challenges with distribution energy resources, the DRs, including renewable energy sources like solar and wind, are pivotal in India's transition away from fossil fuels. However, DRs often face challenges in forecasting their power outputs, as I told a bit earlier, because they are not sure about how much power is available to them in next 15 minutes or 30 minutes. And hence it is very difficult for them to give some assured guarantee of commitment of energy to a computation market, especially when dependent on variable factors like sunlight, wind, humidity, etc. Now, due to which there is an implication of balance issues, that is imbalance issues. Market participants unable to balance their injection and withdrawal, that may face two penalties. For example, I have committed to deliver 100 megawatt through a park of solar and wind, but due to some reason at the time I am able to deliver only 90% of my commitment. So then probably there is a huge issue of balancing, and hence the renewable energy owner will be penalized. And there actually probably the government has to interfere, and because of which actually we cannot promote distributed generations, solar and wind, through private parties, because they always see there is a penalty due to uncertainties, or they have to bid for 80% of its capacity. That is also not a good option. So probably that is an issue that need to be seen. So this presents a unique challenge for distributed energy resources owners due to the inherent unpredictability of their power output. Now, there also need to be a bit of sectoral reforms, power sector reforms. To effectively integrate distributed energy resources, India requires reform in market architecture, grid modernization, and distribution sector rationalization. Investment in information and communication technology (ICT) infrastructure are crucial for improving control over distributed energy resources. Market based economic dispatch, which is a very, very important issue, the Indian government is working towards implementing mechanism like MBED to optimize generator scheduling. MBED aims to create an efficient integrated power sector suitable for the incorporation of variable renewable generations. Now, one of the important issues such as voltage control. Now, due to the integration of renewable generators, the distribution system may face variation in voltage because of the variation in injected power. Now, the voltage within a distribution network need to be maintained within a specific range to ensure the proper functioning of both power system and customer equipments. The acceptable range for voltage during normal operation varies and is specified in various international standards. Now, if you concentrate on a system like IEC, it allows you, the standard reference, which is IEC 610022 low voltage, where 10% plus or minus is being permitted. Whereas in case of GenLec, it is also plus or minus 10%, and the time requirement is 95% of the week must be within plus or minus 10%. Now, if you go to EDF, the standard says for medium voltage it is plus or minus 5 voltage, and for high voltage it is plus or minus 8%. So it is a bit strict. So you cannot afford to go any way more than 5% for medium voltage networks, and must always be within the specified range. However, ESCOM, that is in line with IEC, which talks about plus or minus 10% variation, and the time requirement is not mandatory. Voltage regulation in distribution network is typically managed through two conventional methods: adjusting the source voltage of network substations, which is achieved by employing transformers with tap changers. That is one mechanism. And the other one is the control of the reactive power throughout the system by using shunt capacitor or shunt reactors, series capacitors, synchronous condensers, or static var compensator. Now, the distributed generation can influence the voltage variations in two ways. The first one is DG coordinated with local load. When distributed generation DG align with local electricity demand, it helps to stabilize voltage fluctuations in the distribution network. This coordination ensures that DG output increases with rising demand and decreases with falling demand, promoting a more stable power supply. Now, the DG not coordinated with local load, if the DG operates independently of the local demand, then it can lead to increased voltage variability. For example, high DG production during low demand period can cause higher maximum voltage levels. Means your load is low, penetration is high, that will create high voltage scenarios, while low production during high demand can result to lower minimum voltage level, challenging grid stability. Now, what are the challenges posed by DG to traditional voltage control mechanisms? In a standard high load scenario in India's distribution network, voltage control is typically managed by adjusting the source voltage at substations using tap changing transformers, as we discussed earlier. The presence of DG in certain part of the network can lead to uneven voltage levels, potentially causing overvoltages in areas with DG and under voltages in areas without DG. Maintaining voltage within permissible limit is an important issue with and without distributed generations. So in a distribution grid with distributed generations, unit can be approached through various strategies, that is distribution reducing substation voltages. For example, if you foresee at a distance there are a couple of DGs which are available to you that may increase your voltage scenarios, then probably you can reduce the substation voltage itself. Increasing conductor diameter, operational constraint on DG units, reactive power flow management, advanced technology for voltage management. Power sector can leverage modern communication systems and IT solutions, and these technologies enable real-time monitoring of voltage level across various network points, allowing for more responsive voltage controls. There is one interesting issue, that is power quality, because whenever you integrate your distribution system with distributed generations, you are forced to experience power quality challenges. The effect of the integration of the DG on power quality concerns three major aspects. First one, deep and steady state voltage rise. Second one, voltage flicker. And the third one is harmonics. The IEEE 519 1992 and IEEE 1159 1995 standards outline the compatibility level required by network connected equipment as well as the limitations of emissions from their devices. If these limits values are exceeded, then the polluter may be asked to conduct corrective measures. So this is what being actually given the guidelines. As you could see, the disturbances could be dip 0.1 to zero point 0.9 per unit voltage and duration will be 0.5 to 30 cycles. Surge 1.1 to 1.8 per unit. Dip means basically how much lower you can go from the peak. Surge, that is, well, how much maximum beyond the peak that you can reach and how long they can sustain. That is, zero point 0.5 cycle to 30 cycles. Flicker 0 to 1%, imbalance 0.5 to 3%, interruptions less than 0.1 per unit, harmonics 5%, and they are majorly at steady states. We'll look into those aspects actually with detail in our next lecture. Now, deep and steady state voltage rise. So the first one is steady state voltage rise. Connection of DG to lightly loaded feeders can reverse power flow, causing voltage rise at DG connection points. Neighboring customers may experience increased supply voltage, a steady state effect influenced by X by R ratio, feeder load, and DG's power output. Transient voltage variations. DG can also induce transient effect on voltage levels, particularly with rapid changes in the output. For example, wind turbine responding to fluctuating wind speed can create voltage transients, altering feeder current and voltages. Sudden disconnection, such as wind turbine shutting down at high wind speed, can cause feeder current increases, leading to voltage dip or drops. One more aspect of power quality known as voltage flicker. Voltage flicker refers to a usual sensation of flickering that occurs when there is a rapid fluctuation in light intensity or color spectrum. And it is generally caused by shift variations in load current within a distribution system or within a distribution network. DG adds complexity by causing flicker during large unit startups, sudden output variations, or interaction with voltage control systems. Mitigation complexity varies and is influenced by the frequency and magnitude of DG output that changes. Regulating DG startup frequency and minimizing output fluctuation can elevate flickers. For converter connected DGs, managing startup currents in a practical solution. Modern wind turbines with variable speed designs reduce flicker by smoothing power output changes. The tower shadow effect in fixed speed turbines induces flicker, which is mitigated by adjusting the blade passing and output stability. DGs can improve overall power quality by contributing to fault level and minimizing network impedance changes, thus stabilizing voltage variations. Harmonic and resonances. DG units, particularly power tonic devices, are potential source of harmonics based on their technology and operation mode. Harmonics contribute to increased power losses and can impair the efficiency of both utility and customer equipment. Sensitive equipments may malfunction due to harmonic inferences, posing reliability concerns, equipment lifespan, such that of motors and transformers. Mitigation of harmonic impact can be achieved through modern semiconductor technologies like IGBTs, facilitate the use of higher carrier frequencies, producing cleaner current waveforms compliant with standards. Inverter connected DG units, such as PB system, can lead to voltage waveform distortion and grid resonance issues. Effective harmonic mitigation is achievable through filtering the output current of Poltronics converters. Advances in Poltronics and documented studies shows potential solution to reduce the impact of DG on power quality is possible. Now, when you concentrate on change in short circuit power, DG and fault currents, DG presents typically increase fault current levels in any distribution system. However, the degree of impact hinges on multiple factors: DG capacity penetration, technology, operation mode, and the grid interface. Voltage level before the fault also play a significant role in the impact on fault currents. Fault current contributions vary significantly with the type of DG and proximity to the fault location. Now, the fault current estimators at generator terminals, in case of type of generators, inverters, which are potentially 100 to 400%, separately excited synchronous generators, first few cycles 500 to 100%, and permanent 200 to 400%. Induction or self excited SGs, first few cycles 500 to 1000%, and permanent nearly 0%. Now, slowly we are moving to the protection issues. Protective relays and systems in power systems are designed to isolate faulty equipments, minimizing damage and disruptions caused by the fault. The range of protection devices includes overcurrent protection and burst zone protection. Overcurrent protection prevalent in distribution system typically caters to a one-way power flow from the source to the customers. Now, the issue here, when you have distributed generations connected at wings of the distribution systems, so then probably there could be a chance to experience reverse power flows, okay? Because if the load is less, the generation is more, then the power has to flow back into the feeder. And in that process, the classical protection mechanism which has been designed in the past, where the flow of power takes place from the substation to the consumer side, which is not necessarily true. To accommodate that, the protection technology need to be redesigned, especially systems having distributed generations. Now, DC integration introduced multiple source of fault currents, complicating disturbances detections. DG impact on fault current varies by DG type and connection methods. Converter interface DGs contribute minimally to fault current. Protection challenges in DG inclusive grids, prohibition of automatic reclosing due to DG presence, uncoordinated or unsynchronized reclosing in system with DG, fuse reclosure coordination complexities, issues with islanding operation in DG systems, blinding of protection where DG marks or hides faults, false tripping where DG triggers unwanted protective actions. Now, solutions and strategic for DG protection issues. So, what we need to do, we have to ensure DG units disconnect during fault to avoid any interference with protective systems. Using automated system like SCADA to dynamic protection relay coordination, analyzing data like system voltages and DG output for informed operational decisions. Accurate grid modeling with DG is the key to simulating different scenarios and refining protection strategies. Adopting modern technologies to solve problems like unsynchronized reclosing, fuse reclosure coordination, and islanding. The last section, which we talk about reliability, positive impact of DG. When DG units are installed as backup power sources, they significantly enhance the reliability of power supply. It is very clear when the main grid is not available to you, or the main thermal power plant or huge centrally connected generating units are not available to you, probably through distributed generations locally you can manage some of the distribution loads. That's what we believe, that the reliability of the system increases in the presence of distributed generations. In scenarios like power outage or peak demand, DG can provide critical support maintaining power availability. Now, there are majorly few negative impacts also. If DG integration with the distribution grid is not properly executed, it can paradoxically decrease overall grid reliability. Issues include harmonics, voltage flicker, voltage regulation, and protection coordination challenges. Improperly integrated DG can lead to grid instability and operational difficulties. So, there are a bit of merits as well as limitations. One need to be very careful in installing distributed generations in your distribution system. Now, balancing the equation, despite this potential conflict of having a DG or not having a DG, DG installation can almost always be engineered successfully to benefit utility distribution systems. The key lies in meticulous planning, sophisticated interfacing, and ongoing management of DG units within the grid. Improved dispatch and balancing authority, instant dispatch, lower demand for resource planning, strengthens system and offers across to a broader pool of resources, enables precise matching of demand and generations, reducing the need for costly governing reserves. Now, one more important issue, such as reserve management, modified strategies to handle fluctuations of wind and solar power, because the excess power, how that need to be stored and managed, become an important issue, includes limiting energy ramps and allowing variable resources to provide reserves and other services. Now, energy storage solution is certainly a key for integrating more of variable generations, increasingly popular for reducing generation curtailment as renewable penetration rises. Alternatives include large scale overbuilding, and curtailment to avoid expansive storage systems. The key is also to understand or to avoid forecasting errors. Solar and wind resource forecasting certainly can help the system to improve its reliability, helps in reducing uncertain and enables efficient unit commitment solutions, incorporates both short term and long term forecasting. Distributed resource linking, that is, spreading small distributed resources over a large area, can mitigate the impact of intermittent renewables. That means if you have a huge park, let's say there are 100 wind farms, you know, in a given area, so probably the summation of the outcome of all those wind farms probably experience a smaller variation than having few wind farms integrated to your distribution system. So the intermittency can be reduced by clubbing many distributed generations together. Local variations affect fewer units, resulting in lower overall power fluctuations. Demand response, an effective method to counter rapid ramping issues, can be used for reserves, supplementary services, and peak demand reduction, more cost effective than maintaining extra reserves for balancing renewable energy supply. Thank you very much for your kind attention. Thank you.